Recording in progress.
Good morning, everyone.
Morning.
How was your weekend? Mine was pretty good. I enjoyed the weather. Although, honestly, I didn't actually get out that much, but it's good weather. How about the rest of you? Well, how's your course going so far? We've finished 2 weeks, so we are, 1/8 done with the semester. The way it usually goes is the pace of the first 3/4 of the course seems always kind of like, it seems like we could go faster, and then suddenly, at the very end of the course, I suddenly wonder where all the time went. But we're on to chapter 2 today. Hopefully, if you're watching this, and you're in my you're one of my students, you've already taken the chapter 2 quiz, which is not intended to be something that you take at the end of chapter 2. It's something you take before. Actually, you've read the chapter in the book. You might have some questions, and that quiz is really designed to help you figure out what you know, what you learned from the reading, and what is still unclear to you. Where was I going with that? Oh, so the idea there is, before you attend this live stream or before you watch it, you've taken that quiz and you kind of have an idea about what is still a little bit unclear for the material, and then you can ask those questions during this live stream. But we're on to chapter 2. Chapter 2 is about logic gates, something called circuits. And if you haven't read the book, then you'll have to catch up a little bit as we go through this material. But it's kind of neat because this is really the fundamental hardware and building blocks of an actual modern computer. It doesn't matter whether you're running an old 8-bit computer or a new i9 with 8 cores. They're all kind of built out of the same stuff. Just that over the years, researchers and scientists and engineers have figured out how to make it go faster and faster, and they figured out how to pack more and more stuff into roughly the same area of silicon in your computer. So they can make it go faster, they make it do more, but it's still all just really built out of the same things. So without further ado, why don't we go ahead and get started? So this chapter is more about the actual symbols that we use on paper and on a screen, rather than on the actual physical hardware, although I will show you some of that stuff. But these are what are called the logic gates. They represent operations like and or and not, but these are symbolic representations of them. So this first one over here on the left-hand side is the symbol for and. it has a truth table associated with it. All these operations have a truth table associated with it. So this first one here, if the two inputs are 0, then you get a 0 as the output. In fact, you get zeros for all the outputs except for the last one. So for an AND, the output is a 1 if the two inputs, A and B, are both 1. This next one is OR. Its truth table is a 0 for the two inputs both being 0, and then a 1 for all the others. So if either of the inputs are a 1 or both, then the output is a 1. This next one is NOT. The output is a 1 if the input is a 0, and the output is a 0 if the input is a 1. What is this next one here? Can you tell me what this one is? Actually, if you want, tell me what the next 3 are. Just put them in the chat or something like that. This one here looks like the AND, but it's got this extra little bubble on the end. And this one here looks like the OR, but it's got this extra bubble on the end. Oh, you got it there. So this next one here is NAND. The one after that is NOR, and this last one is exclusive OR. So the truth table for NAND is actually the opposite of it is for AND. So you can kind of think of this bubble as meaning negate. So it takes whatever the output of the AND would have been, and it just negates it. So anywhere where there was a 0 for the AND, there's now a 1 for the NAND. NOR is the same way. It takes the output of the OR and negates it. And then exclusive OR means the output is a 1 if either input is a 1 but not both. So if one is a 1 or the other one is a 1 but not both, then the output is a 1. So we get 0, 1, 1, 0. So by themselves, these logic gates aren't that interesting, but if you connect them up, you can form what's called a circuit. And the circuit also has a truth table associated with it. Here are the 3 inputs, A, B, and C, which are represented in the table over on the right-hand side. We have written down here all 8 possible combinations of the inputs, all the way from 0, 0, 0 up to 1, 1, 1. And then we can calculate the values of this truth table. So you can basically think of the inputs as data going in to this circuit from the left, and then they flow through these other gates, and then they come to the output over here. And so to figure out what the values of the truth table are, you kind of just have to work through all of these 1s and 0s and watch the values flowing through the circuit. So let's start with all 0s, which is the very top row of the table. So the 0 starts flowing this way. It goes through this knot, which means it flips to a 1. And then that 1 then flows down this way and appears as one of the inputs to this first AND. And then this 0 on B flows this way and appears as a 0 over here. This 0 on A also flows down this wire and appears as a 0. And then finally, this 0 on C flows over to that AND gate. Okay, so now we've got a 1, a 0 on the top AND gate, and a 0 and a 0 on the bottom one. Now we can look in the truth table and see what the output of this AND would be, or you could just figure it out, right? So if one of the inputs is a 1 and one is a 0, then we look here in the truth table, and we can see that the output of the first AND is 0, and for the second AND, it's also a 0. And then those flow their way towards the OR. And then we go into the OR with 2 zeros. And so the output is a 0. And now we can write 0 for that first row of the table. Then we'll do the next one. This is where we got 0, 0, 1, which means this 0 on C has changed to a 1, which changes the input to the AND to a 1. The stuff on the top side hasn't changed. A and B didn't change, so nothing changes over there. Does anything change on the output here? So we've got a 1 on this and a 0. So that's this row here, or it's this one, whichever. So the output is still 0, so nothing changes over here, so nothing changes over here. So the output of this is still 0. Then we'll do the next one, 0, 1, 0. So C changes back to a 0. And now B changes to a 1. That's it here. Which means this one changes to a 1. Now we've got a 1 and a 1 going into this first AND, which means the output of the first AND is a 1. This is a 1. And then we've got a 1 and a 0 going into this OR, which means the output of that last OR is also a 1. Okay, so I've just worked through the first 3 entries on the table. Why don't you take a moment to work out the remaining 5 entries, finish out the rest of that table, post in the chat what you get for that last 5. Or actually post in the chat what you get for the whole thing. You should get 0, 0, 1 and then 5 more. Is there a shortcut for this? Not really. I mean, if the circuit is really complex, then you just have to work through all the combinations. I mean, you might be able to look at it and go, well, I didn't change A or B, so nothing in the top changes. I only changed C, so only one thing changes on the bottom, but that doesn't change the output of the whole thing. So you can kind of like analyze it and figure it out, but you really just have to work through all 8 combinations. Have you got it? Still working on it? Andrew's asking, is the whiteboard view supposed to be the main screen? It should be. Is it blurry or is it really small? Since I'm sharing my screen, Zoom should be, making it full screen. Oh, you're looking at it on a phone, so it's kind of small. And you said actually the whiteboard is the picture-in-picture view. No, I wonder if there's a way to flip it so that it's the bigger one. Most of you should be seeing the whiteboard as being like the big view. Oh, you got it. Good job. Okay, we have one person who said the remaining rows are 1, 0, 0, 0, 1. Let me see. So you got 1, 0, 0, 0, 1. It doesn't match up with my notes, but I could be wrong. Anybody else got an answer? We got now 1, 0, 1, 0, 1. That does match up with my notes. 1, 0, 1, 0, 1. So the only difference between those two answers we got was that row right there. Okay, so if you haven't finished that, you can see how the process is kind of laborious. You just have to set the values of the inputs and then watch the data or analyze the data as it flows through the gates from left to right. Now we can come up with an expression also to represent this circuit. There's going to be an OR in the middle. And then on the left-hand side, we have not A and B. And on the right-hand side, we have A and C. And actually, I don't really need parentheses there at all, because the order operations for ands and or says the or gets done last and the ands get done first. Actually, the nots get done first and then the ands, then the ors. But the ors are there, or the parentheses are there just to make it clearer. So we have not A and B, which is the not A here, and the B. And then we have A and C. Here's the A and the C going into this AND. And then the outputs of those ANDs go into this OR, which is the center OR over here. So these logic circuits, these logic gates, you can actually buy from electronics distributor. They look like these things over here on the left-hand side. Each one of these little packages is about 1 inch long, about 1/4 inch wide. And these letterings on the top, if you can see them, those actually tell you what's inside of them. And this first one here is labeled 74, and then there's some letters, but the letters don't matter as far as identifying what kind of chip it is and what's inside of it. It's 74163, which is written right here and right here. And if you look up what the 74163 means, it means that it is a 4-bit counter. So its job is to count from 0000 up to 1111 and then cycle back again. So it can count basically from 0 to 15. The next one over here is a 74138. This is called a 3 to 8 decoder. You input a 3-bit value, anywhere from 000 up to 111, and then it outputs a 1 on one of 8 of these little legs here called pins. So it takes a 3-bit binary value and turns it into an 8-bit value, of which only one of them is a 1 and all the rest are zeros. So if you output like, if you input 000, it turns on pin number 0. If you input 010, which is a 2, it turns pin number 2 on. So that's what it does. And then the last one here is a 7400. This is the NAND. And there's actually 4 of them in there. There's space inside for 4 of them. And so this is called a quad NAND gate because you get 4 of them inside of one little package. You can then take these chips and you can put them on a printed circuit board. And from that printed circuit board, you can then make a useful circuit, something that does something. This picture on the bottom is a picture of the original Apple I computer from approximately 1977. When you bought it, it came basically, I think, as a kit, and you would build the printed circuit board, put all the chips onto it, attach it to a monitor and a keyboard and a power supply, and then you got yourself a working computer. It was up to you to put inside of a case. Most people built like a wooden case and put the whole thing inside of it. So computers from the 1970s and 1980s were typically built from these individual components. Microprocessors back then did exist. In fact, this white chip right here is the, let me draw a line to it. This is the 6502 8-bit microprocessor. It had an 8-bit data bus, which means it could access basically 1 byte at a time, and it had a 16-bit address bus, which means it could access up to about 64 kilobytes of memory. That was the maximum size of the memory that the computer at that time could have. 64 kilobytes, not megabytes, not gigabytes, kilobytes, which by today's standards doesn't seem like much, but that's what they had to work with back then. Applications you were running on the computer were a lot simpler. Games were a lot simpler. The output on the screen was a lot, less colorful and fewer pixels than they are today. You certainly didn't have internet access at all, but that's what computers were like back then. And in fact, you can go right now, you can buy a kit. This is called the Gigatron 8-bit computer. It actually has no microprocessor on it at all. This large chip right here and this large chip over here, those are the RAM and the ROM. The random access memory to hold the programs in, and the ROM that holds other programs in it, the programs that it comes with when you start it up. But all the rest of this stuff, all this stuff over here and over here and over here, that actually implements the processor itself. So this is a kit that you can buy. The printed circuit board costs about $20, and the parts cost anywhere from $50 to $100. And then you can build your own and learn how microprocessors actually work. So basically, what happens is, whether you're loading a program out of RAM or ROM, it basically, comes out of here and flows through here and then flows back. So this right here is called the program counter. That keeps track of what address you're currently executing in the processor. Right over here, this is like the adder circuits. This is called the bus buffer, so it loads data in from RAM or ROM and temporarily holds it in a register until it's able to decode it. And then right here, this is the address decoder. In fact, these little components right here, their job is to figure out what instruction is actually being executed. And there's only 8 instructions in this processor. You can actually see them listed right here. And so what happens is the instruction comes in from memory. 3 of those bits go through this decoder, and depending upon what those bit pattern is, one of those 8 pins goes high, and it says, "Oh, that's what this thing is. This is a add instruction." And then if it's an add instruction, the data comes over here to the adder, where 2 values are added together, and then the data goes and gets stored back in memory. So, like I said, you can actually buy this kit online. It's something that I'm interested in doing, and actually buying one of these kits and putting it together, and you get a simple working 8-bit computer at the end. You can watch some videos online about people constructing this kit and actually using it. Though, like I said, those chips inside, the ones that contain just the fundamental building blocks like ands and ors and nots, typically you buy them, and those chips have like 4 or 6 actual logic gates inside of them. This one over here would be the 7404. This is the 7408, and this is the 7432. This one up here implements the NOT instructions. These are the ANDs, and these are the ORs. So if we were to hook up the circuit the same way I did over on, where is it, on this screen over here, then here's how I would do that. I would take input A, and I would hook it up to one of these NOTs. And then the output of that NOT would go into one of these ANDs. Input B would go straight over to that same AND, and the output of that AND goes over here to the OR. So if I flip back to this screen here, I just did this, and this, and then this. Okay? And then here's input C. And I'm going to do that in a different color. So input C goes over to here. Input A gets pulled off here and also goes into here. And then the output of this AND goes into this OR. And then finally this is the output. Okay, if I can flip back to this drawing over here, I just did A here going into this AND, C going into the same AND, and then the output of that going into an OR. Okay, so yeah, you can actually build these things. And I have a picture of it on the bottom, right here. And here it is. This is the thing you see in the picture. So this over here is I need to move out of the picture so it'll focus on this. So this is a power supply, just so I can hook up a battery to it, and then it feeds power into this. This is called a breadboard, by the way. And it feeds power into these rails up at the top. And then these little red wires here are showing the 5 volts being pulled off these rails and fed into these chips. And then the black wires down here are connected up to what's called ground. So like on a regular battery, like here's a 9-volt battery. You've got 2 connectors on here. You've got one that supplies 9 volts of power and one that's called ground. So anytime you want to connect up something to the batteries, you have to make something called a circuit. So something has to come out of the 5 volts or 9 volts, make a round trip, and then come back to the ground. So as long as you've got a loop in there, electricity can flow. So each one of these chips gets hooked up to power and ground, and that provides the power to the chips. And then these buttons over here, these 3 buttons, are my A, B, and C. This is A, B, and C over here. And then I've got an LED connected to the output of the OR, which is up here. I also have a buzzer so that you can hear it. So when this LED turns on, the buzzer should also sound. If the LED is off, the buzzer will not sound. And then these wires over here, these yellow ones and white ones, are those interconnects that I showed you on the screen here. Okay, so let me hook this up to a battery. So I just have my 9-volt battery here connected to this. And you can see this light here has come on, indicating we've got power to this circuit. And then if I press, let's look at our truth table. Let me switch back to that screen. So if I look at our truth table, if I have all zeros, nothing is happening. If I have a 1 on C, which means I'm going to press the button, this light should come on and the buzzer should sound. And it doesn't. What happened? Oh, right. Sorry, on our truth table, if I have a 1 on C, it doesn't sound. If I have a 1 on B, which is what I meant to say, it'll sound. So if I press the 1 on B, we get the light and the sound. If I have a 1 on A, nothing happens. So only the 1 on B causes a sound. And then let's see, if I have B and C pressed, then I should get a sound and a light, and I do. So both of them pressed. And then what's another one? Oh, A and C. So these two gives me a sound. If I have A and B pressed, I have nothing, right? Nothing happening. And then all 3 of them pressed. Produces the light and sound. Now I should have had this camera up so you could see it. But you could probably hear it, right? So all 3 of them pressed. Light and sound. A and C, light and sound. A and B, nothing. There's a little bit of a chirp because I can't press these buttons exactly simultaneously. But when I do have both of them pressed, nothing's happening. So this implements that logic circuit that we analyzed the truth table for.
Do you know how an AND gate works at like an electrical level? So like if you have how do 2 1s produce a 1, but then like an electrical 1 and a 0 produces 0?
Oh, let me see if I can draw that for you. So basically,
like, is there some sort of like resistor or some switch going on at an electrical level?
Yeah. So let me show you this. So fundamentally, what you've got is I'm doing this as what's called schematic here. So this is a button, and this is also a button. And then here's like, you know, LED. And then over here on the right, over on the left, I got a battery. Okay, so the LED will light up if the electricity is able to go and make a complete circuit. But these buttons are not pressed, so nothing happens. And the LED will only light up if I press both of the buttons. So if I press both the buttons, this will make contact and this will make contact, and the electricity then will be able to flow through. Okay?
Yeah, that makes sense.
So that's
I'm just curious how like electricity kind of presses that button, you know?
Yeah. So what's actually happening is, and I actually have, this was supposed to be part of my demo, but I didn't quite finish it. But hey, I'm glad you brought it up. Where is it? Here. So I actually built the circuits that are inside those chips. And I don't know if you can see them. I don't know if we can focus. Here we go.
Oh, that's cool.
All right, so I wrote a little symbol here to remind me what this is. So this is two AND gates, and it's built out of two transistors, and those transistors basically take the place of those switches. And then there's a couple of resistors here to change whether the electricity flows from the plus side or from the ground side.
Oh.
So what I could do is I could take this, I could attach power over here and ground, just like on the regular chips, connect up inputs A and B, and then connect up a light to the output, and it would light up if I had both those buttons pressed. Or they don't have to be buttons. They could be things like light sensors. They could be something that basically allows electricity to flow if I want it to represent a 1, and impedes electricity if I want to represent a 0.
Okay. So basically, transistors are those buttons that you were talking about.
Yeah. So they allow electricity to flow, or or they impede electricity.
That's really cool. I'd noticed there's like 3 inputs into a transistor, I think.
Yeah, because you have to supply power and ground to it, plus the third one is kind of the button, the finger pushing it.
Okay, that makes sense.
So if the finger is pushing it, electricity is allowed to flow through it. And if the finger is not pushing it, then the electricity does not flow through. And in fact, in the diagram over here, you can see there's basically 3 inputs. You've got this one, and this one. You see that?
Yeah.
Right.
Okay, that's really cool.
Yeah. So basically, this is the third one right here. Is the act of almost pushing the button, if you will.
Cool.
And so I have also this one here. This one's NAND. See, it looks very similar to the AND.
Uh-huh.
And then this one here is OR. Same idea, 2 transistors, and then just resistors in different spots. And then you put them all together, and this one here, this is basically an AND and an OR, and this implements exclusive OR. So I got 1 exclusive OR here. So my idea, if I had completed all this in time, was to also build that circuit, this one here, using just these.
That's awesome. That really makes me want to build it now.
But what I wanted to do was I wanted to attach like little Velcro things on the back, so I could stick them to a board, and then I could just like hold up the board and then connect up the wires and show you it working. But that did not happen this semester. But I did get as far as building this one. I don't know. Maybe
anytime I've ever built anything with the breadboard, it hasn't been that neat.
No.
The DuPont wires are usually pretty long.
Yeah, well, I had them all originally hooked up with those longer wires, and then I cleaned it up. I replaced each one a wire one at a time with these nice ones that are exactly the right length. But but it used to be it used to be a complete rat's nest of wires. Andrew says, yeah, as you recall, transistors work because there's a bit of semiconductive material inside that controls whether electricity can flow through or not. Okay. So here is a skill that I want you to develop. If I give you a circuit like this, I want you to make the truth table and then try to figure out an expression using the words and, or, and not that also represents that circuit. Remember how to analyze the circuit and make a truth table? You just start with all zeros. This is a not here. There's a not down here. This is an OR. This is a NAND. And this is an AND on the very end. If you have all zeros, then the X goes through the naught and becomes a 1. Same thing with the Z. That switches from a 0 to a 1. The Y remains zeros. Then the X and the Y flowing through the OR becomes a 1. The Y and the Z flowing through the NAND, let's see, for a 0 and a 1, we would get a 1 on the output there. And that means we've got 2 1s going into the final AND, which results in a 1 in our output table. So try to figure out the rest of the entries in that table. And then once you get that table, you can try to figure out the expression, or if you kind of get stuck with that, we'll go over it. So while you're working on that, I'll show you this. So I showed you a picture a few minutes ago of the original Apple I computer, which was mostly built out of a lot of these logic chips. There was a microprocessor on there, and there were RAM and ROM chips on there, but the rest of the logic chips were used to kind of glue all of that together. This here is the circuit board from the Apple II computer, which came out a few years later. And this is one that I just bought from someone. So it actually did not come with all the chips on it. And so I've been slowly populating this with the chips. But the processor would go here. I haven't got one of those yet. And then the ROM chips would go here. I still need to get those. This would be the RAM. This would be the memory for it right down here. Again, I don't have those. In fact, the memory for this is no longer available. They're just not made anymore. So what I have to do is I have to find someone who has some of that RAM just sitting around in a drawer, buy it from him or her, and then populate these. But the rest of these logic chips just fit into these sockets, and this makes up the computer. So over here in this section is the video output section. Here's the connector for going to an old style monitor. You know, you've seen probably the back of some of your televisions. There might be 3 connectors on there. One's white, one's red, and one's yellow. So the red and the white ones are used for audio, and the yellow is used for what's called composite video, old style video from the 70s and 80s. And that would have plugged in right here. And then these 2 jacks over here are for, one of them's for audio input and audio output, but used not for like connecting up to speakers, but used for saving and loading programs to a cassette player. You know, those old style music players that use the cassette tapes. You could actually hook one of these up to a computer like this, and you would save and load your programs basically as audio files, audio sounds, to the cassette tapes. So this is a pretty interesting board. Eventually I want to have all this stuff populated so you can see what one of the original Apple IIs would have looked like with all of the chips populated in there. You can still get these processors. I just haven't gotten around to buying one yet. They don't cost very much. A few dollars, but I just have to place the order for it. And then I just got to figure out what chips go into the rest of these slots and buy them. Like I said, the RAM chips I'll have to buy from someone who has some old ones sitting around. Actually, I don't intend to make this a working computer. I just intend it to be something that I can show off. So I actually don't care whether the chips work or not. In fact, you might be wondering, like, do chips actually go bad? And in fact, they do. They eventually do. I mean, a computer like this would be 40 years old or more. And electronics were just not designed to last that long. They probably still will work, but occasionally they go bad. And so I'm hoping that there's someone out there who has some of the RAM chips that went bad on their computer, and they pulled them out, replaced them with newer ones, and maybe I can buy the bad old ones from them and just populate the board with them. The question was that, yeah, that's composite output, not S-video. Regular composite output. Maybe if you have like an old original Nintendo, it would have had composite output on it. Or what else would have composite? A really old DVD player before HD televisions were common, then they would have had composite output to connect to an old style like tube television. Most TVs these days you get still have a composite input on them. The problem is that you've got the composite input going into a digital television, and the output from these computers was strictly analog. And in fact, if you plug them into some of the modern televisions can't really display them at all because they're not displaying a true television signal. They're displaying kind of a fake one. And most televisions stick to the standard so well that they can't actually see the video that these computers output. So you have to connect them to an old style analog television in order to see the picture on them. Okay, we got some people with some results, and if you work it out, you get 1, 1, 0, 1, 0, 0, 0, 1 would be the output from that circuit. And then as far as an expression, let's see. Yeah, I think your expression is correct, Max. But let's take a look. So if I look at this circuit, you know, I can't come up with the expression from left to right. It's just too complicated. So what I'll do is I'll start from the right-hand side and work my way to the left. I know that the very last thing this circuit does is AND, which means there's going to be an AND in the middle expression. I don't know what the left-hand side or the right-hand side is yet, but I know there's going to be an AND in the middle. And let's just say that the left-hand side of the expression represents what's going on towards the top of the circuit, and the right-hand side of the expression is what's going on in the bottom side of the circuit. I know there's going to be an AND in the middle. I don't know the left-hand side yet. I don't know the right-hand side yet, but let's work on those. Now, going into the AND on the left-hand side is going to be an OR. Again, I don't know what's going into the OR, but I know there's going to be an OR over there. So I know it's going to be something OR something, and something NAND something, which represents the bottom side of the circuit. Again, I don't know what these blanks are, but I'll work on those. So we're starting out with the AND in the middle with two blanks on either side, and then we're going to successively try to figure out what goes inside of those blanks until we arrive at just single inputs in those blanks. So let's work on the next ones. This first OR over here represents this connection, and that comes from not X. So I know I can fill in that blank with not X. And then the right-hand side, which is the bottom connection, comes from Y. So there's a Y over here. Let's work on the NAND now. The left-hand side of the NAND, which is the top one, comes from the Y. So I know there's a Y over there. And then the bottom side comes from this not Z. And that's the expression. So we got not X or Y, and Y or not Z. And you know, if you wanted to, you could further break out this NAND into an AND with a not in front of it. So basically bring the not out in front. But because the circuit itself contains a NAND right here, I'm going to leave it this way. Okay, so that's one skill to develop, which is start with the circuit and then make the truth table and then derive an expression. Let's flip that around, and this time we're going to start with the truth table, and we're going to derive a Boolean expression and then draw the circuit. So we're kind of like go in a reverse direction. So here's how you do this. With this truth table, you should focus your attention on the rows that have a 1 as the output. That's the first one, the second one, the fourth one, and the last one. So just look at the table and ignore all the ones where the output is a 0 and just look at the ones where the output is a 1. And then write an expression for each one of those rows. The first row is a 1 when A is 0 and B is 0 and C is 0. Let me say it another way. The output is a 1 when A is false and B is false and C is false. You hear the word and in there? So we have not A and not B and not C. Okay, so this expression, not A and not B and not C, will be true when A and B and C are all false. For the second row, this one will be true when A is false, so we're going to write down not A, and B is false, so we'll write down not B, and C is true. We just write down C for that. So you can almost just look at the ones and zeros on the input column and write the expression over here. Everywhere where you see a 0, you put a not. Everywhere you see a 1, you just leave the input as is. For the fourth row, we've got not A and B and C. And then for the last row, we have A and B and C. Okay, all ones over here. So no nots anywhere in the expression. Another way to say it is the output for this last row is a 1 when A is true and B is true and C is true. So A is true and B is true and C is true. And finally, just connect these all together with ORs. So you end up with this big, long expression, but it works. So the output of the circuit is a 1 when the first expression is true, or the second expression is true, or the third one is true, or the fourth one is true. So if either one of them or any of them is true, then the whole thing is a 1. The whole thing is true. This is called, the way I've written it here, this is called sum of products form. SOP. Sum of products. Basically, if you have a whole bunch of ands connected by ors, it's called sum of products form. So the only operators you're going to use are nots, ands, and ors in the sum of products form. We ended up with this big, long expression. You may be wondering, is there a way to simplify it a little bit? And yes, there is. Here's the way I would do it. I would look at some of the pairs of expressions and see if I can simplify those a little bit. If I look at these first two, and I look over here at the table, I look to see what's in common between those two rows in the table? If I just look at these two right here, what's in common between them? Well, what's in common is both A and B need to be 0. C could be either a 1 or a 0, so it doesn't matter what the value of C is. All that matters is that both A and B are 0. And these are the only two rows where that's the case. All the other rows here have 1s in either A or B. But these are the only two rows where both A and B are 0. So I can simplify this expression and say not A and not B. Hopefully you can, let me move things over a bit so they're not so squished. My wife just poked her head in here. All right, and then let's look at the last two rows here, or not the last two rows, these last two expressions. I'm trying to draw a straight line and it's not coming out. There we go. So what do these two rows have in common? All right, so you look at these two values here, and what I see is that both B and C are 1. A can be either a 0 or a 1, so its value doesn't matter. It doesn't matter whether A is a 0 or a 1. What is true about both of them is that both B and C are 1s. And those are the only two rows where that's the case. So now we can just connect those two together with ORs, and we've got a simpler expression. Instead of having 4 terms in it, each one of those AND expressions is called a term, it's only got 2. So now we can draw a circuit based upon that simplification. I've got an OR at the very end. This is my output here, and that represents this OR. Then on the top side, I have A going into a NOT, and B going into a NOT, and then those both go into an AND. And then for the bottom, I've got an AND. I have B going in without going through a NOT, and then C going in also not going through a NOT. And the output of that AND goes into the OR. And I'm not sure, let me see over here. Oh, I'm looking at my monitor over here, and it looks like my little picture-in-picture does not cover up any of the text. So that's good. I was worried that over here in this corner, my little picture might cover up some of that, but it doesn't. Okay, so notice here that this truth table is the same as this truth table. Okay, same truth table, but the circuit is different. So it's possible that the same truth table might have 2 or more circuits that implement it. And what that means is that if 2 circuits implement the same truth table, or they have the same truth table, then those 2 circuits are said to be equivalent to each other. If I show you 2 different circuits and I ask, are these equivalent to each other? Then the way to figure that out is to construct the truth table for both of them and see if they're the same. If they are, then those two circuits are equivalent to each other. It doesn't matter whether they look different or whether one's simple and one's complicated. As long as they have the same truth table, they're equivalent. Imagine what the circuit would have looked like for this expression. You would have had a whole bunch of ands over here on the left-hand side, pulling in all three of those values. You would have a whole bunch of ors connecting all of those together. So it would be a really complicated circuit, but it would implement the same truth table, and so it's equivalent. So you're saying the truth table is not correct? For which one? For this one over here? Oh, you hooked it up in Logisim and you didn't get the same answer? So you're talking about this one or this one here? This one over here. I'm a little confused. You're saying the truth table is not correct. Okay, but on this screen, I gave you the truth table and we came up with the circuit. It was on this screen where I gave you the circuit and we came up with the truth table. So I'm curious. Let's see. You said the last row and the second row are supposed to be zeros. So let's just try that out. It says right here, this should be a 0 and this should be a 0. Let's give it a shot. So let's put in a 1 here for Z, which represents this row, which means that this becomes a 0. And then we have a NAND here. 2 zeros going into a NAND gives us a 0. Oh, you're right. Let's see. What's going on here? And that goes into an AND. And if we have a 1 and 0 going to AND, then you're right. That should be a 0. Huh. You know, to be honest, I'm just going over some notes that I have. And these notes are like years old. I've been using the same example for years. So I'm wondering if somewhere along the line I made a mistake and I didn't draw this circuit correctly. Like one of these things was supposed to be different, and I messed up because it looks like if this is a 1, then this is a 0, this is a 0. Let's see, we have 2 zeros going to a NAND, then we have a 0 on the output. And then that means we got a 0 here. Nothing changes over here, right? So this is still a 1. And so this should be a 0. So you're right, there should be a 0 right there. Huh. Doesn't 2 zeros into a NAND give a 1? Oh, wait. Oh, wait. You're right. 2 zeros into a NAND gives a 1. You're right. Yeah, that's a 1. So that's a 1. Yeah, so there's a 1 there. Okay. Yeah, that's right. And then the last one, which is all 1s, so we got a 1 there and we got a 1 there. That means there's a 0 here, there's a 1 here, and a 1 here. Okay, if we go through the OR up here, this is still a 1. We have a 1 and a 0 here, which is still a 1. And so we've got a 1 and a 1 here, and we got a 1 here. So that should be a 1. That wasn't a 0. That was a circling it to say that's still correct. All right, now I'm curious. Right, so he said he hooked it up in a program called Logisim, which basically allows you to hook up logic circuits and see what they produce. So we're going to bring out my computer, hook it up, and we can try that. Give me a moment to hook this up. Let me find Logisim on here. Okay, with this program, we can basically hook up this circuit. So let me put in my inputs. So here is X, Y, and Z. And let me label those. And then we've got a NOT right here, and another NOT right here. There's an OR here. Got an AND on the end, and then we have a NAND that I need to put in here. Now with Logisim, the gates by default have 5 inputs. Any input you don't connect just doesn't matter. I could change the number of inputs, but I just won't connect the ones that I don't need. And then here's my output. And then we'll start hooking this up. Okay, that should be the circuit. And if we just punch the buttons here, we've got 0, 0, 0 producing a 1. We got 0, 0, 1 also producing a 1. Here's 0, 1, 0 producing a 0. So far this matches. If I bring this up here. So I've just done the 3rd row in the table. Then we do the 4th row in the table, 0, 1, 1. It comes out to be a 1. That's good. The 5th row is 1, 0, 0. We get a 0. So 1, 0, 0 produces a 0. 1, 0, 1 also produces a 0. 1, 1, 0 produces a 0. That matches. And then 1, 1, 1 produces a 1, and that matches. And actually in Logisim, you can also say project analyze, and then table, and it produces the truth table for us. And this matches the table that we came up with doing this manually. So it does match. That's good. That means my notes are correct. I think. Oh, what you're saying is that maybe you accidentally put an and up here instead of an or, and that was causing your analysis not to work out, or Logisim's analysis not to work out. All right, let me let you in on a little. Actually, maybe I'll do this later. What I want to show for you right now is a video. This was done by a fella named Ben Eater, who's got a great YouTube channel, and in this channel, he shows you how to build an 8-bit computer basically from scratch, right? He starts with the individual logic chips and builds it up from there. And towards the end of the video series, which I don't think is entirely done with, he ends up with this giant computer on all these breadboards. It must be about 2 feet tall and about 1 foot wide with all these logic chips on it. And it basically just implements all the different parts of the microprocessor, along with the little LEDs for displays and buttons for inputs. It's a really great series. And I'm going to show you the video where he constructs an adder to actually add up 2 4-bit numbers and produce the sum of them. So let me get that video set up here. And then we'll watch it.
So if we want to add 28 plus 22, it's pretty simple. 8 plus 2 is 10, so we put the 0 down here, carry the 1. 1 plus 2 is 5. It's 50. Okay, simple enough. Now if we want to do that with binary, it actually works pretty much the same way. So we line up all of our columns, and so 28 in binary is 11100, 22 is 10110, so we've got that converted. We line up the columns, we just go column by column. So 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 in binary is 2, but we don't have a 2 in binary, so we write it as 1, 0. So the same thing we did here with the 10. Here we do the same thing. So we put a 0 down here and carry a 1. And that's how we write a 2. Here again, we've got 1 plus 0, which is 2. So we write that in binary again by carrying the 1 and putting the 0 down here. And then finally, 1 plus 1 is 3, and in binary, a 3 is 1, 1. And here we end up with the binary representation of 50. So the same algorithm works in any base, which is kind of cool. And so now if we want to build a circuit that does this for us, really it's actually a lot easier, I think, than regular arithmetic, because you only need to know a couple facts. And this is everything you need to know. And so if you can build a circuit that does all of this, then you can add a single column, because you've got the A and B, which is just the first number and the second number. And then you might also have this 1 that sort of carries in from the previous. So if you've got all that, then we should be able to add some numbers. So let's think about how we would build a circuit that kind of does this. And one way to do it is just kind of break down inputs and outputs. So we have the inputs A and B, and then we have these 2 outputs, which are the sum that you put down here at the bottom, and then the carry. I'll call this the carry bit, because you would carry that bit over to the next column. So if we look just at the case here where we've got 2 numbers that we're adding, so we haven't carried something in from a previous column, and we look just at the number that we're putting down at the bottom here, this actually looks a lot like an exclusive OR, right? Because if A or B is a 1, then this last bit here is a 1. If A or B is a 1, but not both. So we can actually start to build this, right? So we can have an exclusive OR gate here. This is how you draw an exclusive OR. And we have our A and our B coming in. And then coming out is going to be this right here. Now what about the second bit, the carry bit here? Well, this is also pretty simple because it's always going to be 0 unless A and B are a 1. And so that's just an AND gate. So I can have an AND gate here. AND gate. And just take this same A and B input that we had over here, bring it into the AND gate, and this will be this, this bit here that we would potentially carry over into the next column. And so this actually is enough to add two numbers. This covers all of these cases here because we have our A and our B input, our two inputs, and we have our two outputs here. This is this first output, and then this here is the second output. It gets a little bit more complicated now if we have a carry coming in from a previous column, because it's not enough to just be able to add two digits, because as soon as we get to this 1 plus 1, then we have to carry a 1 to the next column, and in the next column we have to deal with three numbers. So let's just kind of add this case where we have this carry that might be a 1. Well, in that case, if we look at the last column here, it's actually the inverse of the case here. So really what we want to do is we want to invert this output here whenever the carry bit is set. And a clever way of doing that is with another XOR gate, because when you XOR something with a 1, it will invert it. So if we have our carry coming in here, we send that into the XOR gate, and this will be the sum that we put at the bottom here, because what happens is if this is a 1, then a 0 XOR 1 is going to be 1, a 1 XOR a 1 is a 0, a 1 XOR a 1 again is a 0, and then here we have a 0 XOR a 1 is a 1. So this will give us this last column. Now for this first column, which is the carry bit that that we might put into the next column, we've got these cases covered, right? Because if A and B is a 1, then we get our 1. And we even have this case covered here, because if A and B is a 1, then we have a 1 here as well. But what we don't have covered is these two cases here, where A or B is a 1 and we have this carry. And so what we can do is we can actually say, well, if we have the carry exclusive OR A or B, we already have that exclusive OR A and B. So if A or B is a 1 and we have the carry, then we want this 1. So we can actually just AND the A or B. So this is A or B we already have, and the carry bit is set. Then we get this 1 here. So now we have this case. Now we have these two cases covered by this output of this AND gate. Whoops, we want to bring the carry bit in there as well. And we have these two cases where it's 1 covered by this AND gate. And so really what we want to do is we want to say that this bit is going to be a 1 either time this condition or this condition is met. So we can use an OR gate. So this is an OR gate. This is an AND gate. This is an XOR. So you guys don't get confused here. And then this is the carry. And so this actually is what is called a full adder, because we have A and B, so we have two numbers that we're trying to add. We potentially have a carry from a previous addition, and then we get a sum out, which is the number we put here at the bottom, plus we get a carry that goes into the next column. And so with this sort of simple circuit, if we build one of these circuits for each column, we can add as large a number as we like, as long as we keep building as many of these circuits as we like. And so, for example, I've drawn up this diagram here, which shows that same circuit sort of replicated 4 times. And in this case, you have an A and a B coming in here, and the carry coming out goes into the carry of the next circuit. So this is sort of like when you're actually doing the arithmetic here, you have a 1 plus a 1, you have a carry, it goes in as an input to the next addition. And so that carry comes into here, along with a new A and a new B, which is going to be the A and B for this column, for the second column. And then you have a sum coming out, which would be the number down here. And then you have that carry going over, which goes into the next column, plus the new A and the B for that column. Carry comes out, and so forth. And so here I've drawn 4 of them, so we can add 2 4-bit numbers, but we could keep building more and more of these if we wanted to. So to actually build this, we can use some pretty simple components, because we have XOR gates, And these chips here actually implement XOR gates. And here is the data sheet for them. And so you can see from this data sheet, basically each of these chips has 4 XOR gates built onto it. And so, you know, to build a 4-bit adder like I've drawn out here, you need 1, 2, 3, 4, 5, 6, 7, 8 XOR gates. So we have 2 of these chips. Each one has 4. We also need some AND gates. And so there's another chip that has AND gates. We need 8 of those. And so each of these chips has 4 AND gates, as you can see on the data sheet. So we got those. We also need some OR gates here. We just need 4 of those. So there's another chip that has 4 OR gates. So we got that. And then a couple other things that we need. We need a breadboard to build this on. So we're going to build this on this breadboard here. For the inputs, I have these little dip switches. And so each of these has 4 little switches on it. And that'll let us set the 4, you know, the A0, A1, A2, and A3 for the one number that we want to add, and then another one for the B0, 1, 2, and 3 for the other number that we want to add together. And then finally, a couple other things we need are some kind of outputs here. So we have our sums coming out here. And so I just have some little LEDs that'll light up for each of these digits. And I have 5 of them because there's 4 outputs plus the final carry, which is, you know, because if you're adding 2 4-bit numbers, you might end up with a 5-bit output. So that last carry will have another LED for that. And then I'm just going to power it with a little bit of a little USB. This is just a standard USB charger that I've kind of hacked the end off of and just taken the red and black wires out of there, and that'll give us 5 volts. So I'm going to go ahead and start getting this thing built on this little breadboard here. And I'll just start by sticking this stuff onto the breadboard. Okay, at this point I've got everything on the board and all the chips are powered. So each of these chips has a VCC, which is the positive voltage, and then the ground. So each of those is connected for each of these chips. Everything's on the board. So I'll go ahead and just actually just wire up the first of the adders, and we can kind of play with that one first, and then we'll do the rest. Okay, so I've got the first stage of this wired up. I think we'll see. We'll power it up and see what happens. But so I'm using I'm using 2 of the XOR gates on this chip, 2 of the AND gates on this chip, and then the OR gate is over here. So I've got some kind of wires running back and forth. But I guess as I do the additional bits, hopefully the wires will get a little shorter, so it'll all fit. But in any event, this is the sum of the first 2 bits over here, and this will be the carry. So let's get the power. I've got it already plugged in, so I'm going to just hook this up here and see what happens. And that's not good. Oh, I'm not done yet. Okay, now I think I'm done. I just had to hook up a couple extra connections here because the switches weren't fully wired in. Okay, so now we add power and everything is off because these first 2 bits are off. And if I toggle either of these on, hopefully, yes, we see 0 plus 1 equals 1. So this is a binary 0, 1. So this is the answer there. If we turn this off and turn the other one on, we see again 1 plus 0 also equals 1. That's good. And if we turn both of them on, we get 1 plus 1 equals 2. So it looks like this is working. So now I'll go ahead and just wire up, I'll actually wire up all the remaining 3 adders, or the remaining 3 adders for the remaining 3 bits here. Okay, so I just finished this, so let's see if it works. I've been testing it as I go, but I haven't tested the whole thing all together. But let's see how it does. If we plug this in, we've got zeros and zeros, so we've got all zeros on the output there. So let's see if we want to do some arithmetic here with this. Let's imagine we want to add 10 plus 7 and get 17. So in binary, this is 10, this is 7. So we would add 0 and 1, and we get 1. And we add 1 and 1, and that's 2, so that's a 0, carry a 1. 1 and 1 again is 2, so 0, carry a 1. 1 and 1 again is 2, so that's a 1, 0 in binary. So this is what we would expect. So let's go ahead and give it a try. So 10 is 1, 0, 1, 0, so we can do 1, 0, 1, 0. And already you see the output is 1, 0, 1, 0 because we're adding that to 0. So 10 plus 0 is 0. So far, so good. And then 7, we can do 0, 1, 1, 1. So if we do 0, 1, 1, 1, there we go. We get 1, 0, 0, 0, 1. 1, 0, 0, 0, 1. So it looks like it's working.
So he's got a whole series of videos in which he does that. This is his website, eater.net, and then this is 8-bit/ALU, which stands for Arithmetic and Logic Unit. And then he's got a whole bunch of videos where he constructs an ALU from just discrete logic chips. Very cool. If you need the URL again, it's right here. It's eater.net/8-bit/ALU. We can watch the first video. That's the one that we just watched. I got one more thing to talk about, and then we'll be done for today. And that is that the NAND gate is actually what's called a universal gate, which means that you can construct all the other gates out of just that one. Now I'll quickly show you how to build NOT, AND, and OR out of the NANDs. And then once you have those, you can also build all the rest of the gates. So once you have NOT, AND, and OR, you can build the rest of the gates. So what we have to do is show that you can build NAND. You can use NAND to build just these things here. So for the NOT, what we want to do is we want to build this. We want to build it so that if you input a 0, you get a 1. If you put a 1, you get a 0. So let's look at the truth table for NAND. So here's the truth table for NAND. If we kind of look at this truth table and just look at the, whoops, that's too big. Oh, I forgot how to make that smaller. Oh, here we go. We just look at the first row and the last row. You can see there that if both the inputs are 0, we get a 1 for the output. And if both the inputs are a 1, we get a 0 for the output. So it's almost like these first two rows, the first row and the last row, represent the operation we want to do. So that's how you can build a NOT out of NAND. You start with your NAND, and then you just feed the same input, the one input, into both of the inputs to the NAND. So if I feed in a 0 here, I'll get 2 zeros going into the input and a 1 on the output. And if I feed in a 1, I'll get 2 zeros whoops, not a 1. If I feed in a 1, I'll get 2 1s going in, and I'll get a 0 coming out. So that's how you build a NOT out of a NAND. You just need a single NAND gate, and then you just duplicate the inputs, and you've got yourself a NOT. Okay, so once we've got the NOT, we can now build AND out of NAND, because really, what a NAND is it is an AND with a NOT sitting on the end. So if I take a NAND and I feed it through a NOT, then I've got myself an AND, right? I'm basically taking the output of the AND and I'm NOTing it, and then I'm NOTing it again. Well, I know how to build a NOT. It's just this one. So I'm going to swap this circuit in for this one here, and that gives me a NAND feeding into another NAND, and that last NAND implements the NOT. And this is what gives me my AND gate. So this is NAND followed by NOT. Now I've got NAND here followed by NOT. Okay, so I can build AND out of NAND. I just need two NANDs, and I can build AND out of that. And then finally for OR, let's look at the truth table for OR. And here's the one for NAND, just for comparison. It's also written up at the top, but I'll put it here as well. And if you look at the output columns for OR and NAND, you can see that they are just flipped. The output for OR looks just like NAND, but it's upside down. And the way you flip a truth table over, just end for end, is to invert the inputs. So when you invert the inputs, the last row becomes the first row. The third row becomes the second row becomes the third row, and the first row becomes the last row. You can see the input columns here are just the same as the input columns from the other table, but they've been reversed. So what we have to do is invert the inputs coming into a NAND. And that gives us our OR. Well, we know how to build two NOTs, right? You just use NANDs for that as well. And this is our OR gate. So we've shown here that you can build NOT, AND, and OR out of just NANDs. And that's in fact what chip manufacturers do. When they want to construct a microprocessor or any kind of integrated circuit, what they do is they basically got the equivalent of a rubber stamp that just stamps out NANDs all over the place. And then they just hook those up. And in fact, that's one way to build a programmable chip. It's just basically a grid of NANDs. And then you can electronically connect up those NANDs in different ways and construct any circuit that you want. They're called things like programmable logic arrays or field programmable gate arrays. Basically, they're just a whole bunch of NANDs, millions of them, but they're all just sitting in a grid. And then you can use a special programmer circuit that internally hooks up those NANDs in the way that you want, and you can implement any logic circuit that you desire with basically as many inputs as you need. Not as many, but usually these chips have like about 50 or 60 inputs coming into them, and then you can use those 50 or 60 inputs to construct any kind of logic circuit you want. So you could actually take one of these logic arrays and you could build a microprocessor out of it. Once you define how that microprocessor should work, and you can use some of the instructions you saw on Ben Eater's videos, then you can build your own microprocessor out of these logic arrays. And so NANDs are extremely cheap to manufacture. As you saw, they just need two transistors and a couple of resistors, and then that's it. You've got yourself a NAND gate. And that's why they just build them out of NANDs, because they're cheap to manufacture. You just rubber stamp them all over the place on your microprocessor and then just hook them up the way you want, and you can build your processor that way. There's a tie-in with NAND flash as well. It turns out NAND is a universal gate, and so is NOR. NOR is also a universal gate. And you can go through the same analysis, a similar analysis, to show that NOR can be used to build all of the logic gates. So what's the difference? Why NAND versus NOR? Well, it turns out NAND is cheaper to manufacture, right? You only need two transistors and like a resistor to do it. NOR, I think, is more complicated to manufacture. You might need like 3 transistors to do it, or Or you can do it with different kinds of transistors, which are themselves a little bit more expensive to manufacture. So NOR costs a little bit more, and NOR also consumes more power. Wait, is that true? I'm trying to think now. NAND is cheaper. No, sorry, the NAND consumes more power. The NOR consumes less power, but is more expensive to manufacture. And so that's really what it boils down to, is for the manufacturer of like an SSD drive, they're going to choose to make out of NANDs because they're cheaper. But the downside is they consume more power. And so really, you, the consumer, bears the cost of that, right? You buy the SSD for less, but it costs more to run. You can buy a NOR SSD, and it'll be more expensive, and it will also be faster. Right, NOR gates are actually faster than NAND gates, but they cost more. So there was a time, not too long ago, maybe, well, when SSDs were first coming out, roughly 10 years ago or so, when you could actually buy both kinds of SSDs. You could buy NAND SSDs and NOR SSDs. The NAND ones were cheaper. The NOR ones were more expensive, and they worked faster. So the NOR ones were kind of like for enterprise environments, data center environments, where they could afford to buy more expensive SSDs, and they were as a result they were faster, so they're good for like things like servers. Whereas the NAND SSDs were better for consumers, right? Cheaper and not as much, not a little bit slower, and of course they don't get as much usage as a server one does. These days, the technology for the NAND SSDs has caught up basically to the point where they're fast. They don't consume nearly as much power. They're much more reliable. And so NOR SSDs have pretty much just fallen by the wayside, right? The NAND SSDs are so good now that it's basically what you buy. It's just the NAND ones. So they're cheap to manufacture, and they're fast, and they consume less power. It's just because technology has moved forward. So yes, there is a tie-in with flash drives and SSDs. Any other questions? So I went over time a little bit today. Hope you don't mind. Oh, you have more questions? Oh, how does a NAND store information? Well, there's a fundamental circuit called a flip-flop you can get, and that's where you basically have two NANDs and they're cross-wired. So the output of one becomes the input to the other in this weird kind of figure-8 fashion. And that can be used to store a bit of information. Because of the feedback nature of it, basically if you put a 1 into that, the 1 stays there because basically the output is feeding back into itself. And if you put a 0 in there, it also stays in there. So it kind of gets trapped inside this circuit. So that's called a flip-flop circuit. And that can be used to store information. So you can go look that up. Actually, I can quickly show you a picture of it. Let's see if I can look this up. Just do a quick Google image search. And you can see here's that figure eight drawing. And so you can put I think you hold these as both 1s, and then it stores the bit. And if you put a 0 in on the S side, then it outputs a 0 over here. And if you put a 0 over here, it outputs a 0 over here, or outputs a 1 over here. So this is called set and reset. So you hold it at 1 in order to store the bit. And this is why NANDs use more powers, because you have to feed a 1 into them all the time in order to hold the data. For a NOR, you feed in zeros all the time, and it holds the data. So NORs use less power because you're feeding a 0 in instead of a 1. Okay, and then so you hold them both at 1s, and then if you briefly put a 0 over here, it'll store a 0 in the circuit. And then if you briefly put a 0 over here, it stores a 1 in the circuit. So it seems kind of strange, right? So basically it's a set and reset. So you can set the bit to be a 1, or you can reset the bit back to a 0. and whichever one you set is what gets stored. Here's actually the truth table for it. So if you put both ones, there's no change to the output. If you briefly put a 0 on the set, then the output of this one becomes a 1. And if you briefly put a 0 on the R, the output becomes a 0. And then you should never put them both at zeros. This results in an invalid state where the bits just change. They sort of flip back and forth really quickly, but you should never put both zeros in there. So hold it with 2 ones, and then you can set or reset the bit with zeros. And that's basically how you store a bit. So that's sort of the... Now that's not the way that modern computers store bits in RAM. RAM is actually built up out of little tiny capacitors, which can be used to store a charge. Capacitors are super cheap to build. Super, super cheap. The problem with capacitors is that they lose charge over time. And so with modern dynamic memory, you store a 1 by charging up the capacitor, and you store a 0 by discharging the capacitor. And then periodically, like 10 or 15 times a second, you have to go through and recharge all the capacitors. And so that's called the dynamic memory refresh. And so your processor actually has to pause for a moment while that's happening, and it slows down your computer a little bit. There's also a style of memory called static RAM. And this is an older style before dynamic RAM sort of took over the market. And static RAM is built up out of these flip-flops. So they consume more power, but they can hold their own memory. Right, so as long as you're supplying power to a static RAM chip, it holds the memory. You don't have to go through and refresh the memory periodically like you do with dynamic memory. And because static RAM memory is made up of these flip-flops, there's a limit to how much you can pack into one chip, whereas dynamic memory, being built up out of capacitors, you can pack like billions of those things into a little chip and store, a gigabyte of memory in one, or a gigabit, if you will, in one chip, or even more. You can store 8 gigabits or 32 gigabits now, so there's just huge amounts of memory you can pack into one, whereas static RAM, well, it's not used much these days, but, they max out at like 32 kilobytes, 64 kilobytes or so. And mostly static RAM is used for embedded applications, like, like your toaster oven, right? It's got a little computer inside of it. It probably has a static RAM chip in there for holding the memory. You don't need much. You just got to hold what? Temperature, timer, what mode you're in. That's it. Like a few bytes, that's all you need. So they don't have very much memory in them. Yeah, with the static memory, as long as you supply power, it will hold the memory indefinitely. Static RAM is not like flash RAM, or flash memory, where you can store it and then take off the power, and then it will keep that memory almost indefinitely. The question is, do they technically never wear out? Yeah, they'll essentially last. I mean, up to the limits of manufacturing, they'll last almost forever. There's still computers in use that have static memory from 40 years ago that are still working. That Gigatron computer that I showed you has a static RAM chip in it because it doesn't need very much. And also, you don't have to go through and refresh the memory periodically, so you don't have to spend any CPU time keeping the memory. You can spend all your CPU time playing games or whatever. Actually, with that Gigatron, it spends most of its time putting the graphics on the screen. So the way the computer is it paints the picture, and then I think every 4th scan line of the picture is just all black, because that's where the CPU is actually doing its computations for like the game or whatever it is you're playing. And the other 75% of the time, it's putting graphics on the screen. The Gigatron outputs, yeah, it outputs an RGB VGA signal. So you hook it up to an old style VGA monitor. You can see some videos online about Look for the videos by the 8-bit guy. He's got 2 videos on the Gigatron, one where he builds it, and the next one where he upgrades it to play more games and have a basic interpreter and be able to program it. So there's 2 videos you can watch. But he also explains how the scan lines work a little bit and how you can change the number of blank scan lines and speed up or slow down the computer. I'm doing a quick search here.
Our new EV rental fleet is the absolute GOAT.
Nice. Speaking.
I didn't mean to do that.
In March of 1971, Intel released the very first microprocessor onto the market. It was called the 4004. This, along with the 8008 processor released the following year, helped to jumpstart the computer revolution. But does that mean there were no computers before the microprocessor? Well, we know that certainly wasn't the case, as computers such as the digital PDP-8 had seen widespread use in businesses since the 1960s. In fact, the guidance computers used on the Apollo spacecraft were also designed in the 1960s. And let's not forget the famous story of Steve Jobs and Steve Wozniak creating the arcade game Breakout, which was also made entirely of TTL logic chips. Of course, digital computers were in existence as far back as the 1940s using vacuum tubes, so needless to say they didn't have microprocessors either. In fact, if you think about it, a microprocessor itself is nothing more than a bunch of transistors, which in many cases can be separated into distinct sections of logic units. Just as an example, the 6502 processor was recently recreated in a large format with a bunch of transistors and a lot of blinking LEDs to make it look cool, and so you can see what's going on inside of it. They're calling it the Monster 6502. So now I'll introduce you to the Gigatron TTL microcomputer kit. This is another do-it-yourself computer kit, similar to others I've featured on the channel before, but the main distinguishing difference is that this one has no microprocessor. It comes in a very neat looking little box and a fantastic manual. I'll go as far as to say this is the best manual I've ever seen for a project like this. And while it does contain a lot of in-depth schematics and stuff, don't let that scare you away, as the assembly instructions are actually really simple and anyone should be able to assemble this. In fact, the only tools you'll really need is a soldering iron, preferably a good one, and some rosin core solder, and a pair of wire cutters, and that's it. So just taking a look at what it comes with, here's a bag with most of the smaller components, and then here are all of the TTL logic chips, along with a RAM chip and an EEPROM. This appears to be a ubiquitous USB power cable. And the board itself. The layout on this board is spectacular, and I can tell a lot of attention was taken to make this look nice and be easy to assemble. And down in the corner it says the computer without microprocessor, along with the main specifications. I'm going to follow the assembly instructions in the manual, and it says I should start by installing these 40 little capacitors. And so that's what I'll do. There was a little confusion in the manual on how to install these diodes. I had to read it several times, so hopefully this is right. Well, the manual says at this point I can power it up, and if I see the test pattern flashing on the LEDs, then everything's working so far. And it looks like it is. So I guess I got the diodes in right. Next I'll install the audio output. And we'll need the joystick port. And the last thing is the VGA port, along with the various circuitry that goes along with that. After spending many hours assembling this, it was time to actually test it for video output. So, crossing my fingers. Hey, it works! So for final assembly, I just need to install these rubber feet on the bottom of the case, and then 4 more rubber feet go inside the box at the corners, and the board actually rests on these. And then I can just insert the board and close it up. It's definitely a thing of beauty. Well, let's see what we can do with it. When you first power it up, you get a menu of some test programs you can try out. I'm going to start with pictures. Interesting. Some kind of ape. I'm not sure which species. Anyway, the Gigatron can display 64 colors because it has 2 bits for each of the RGB channels, which I noticed when I was soldering in the resistors. And while the resolution is very low, the colors are actually quite nice. So let's talk about the video display a bit. The Gigatron can display a video resolution of 160 by 120 pixels, which is less than most 8-bit computers. However, the Gigatron doesn't really have a video chip. They've borrowed a page from the Sinclair ZX81, and all of the video generation is handled in software by the CPU. Of course, in this case I use the term CPU somewhat loosely. And due to the clock speed of this machine compared to the speed of a VGA signal, 160 pixels is the best resolution that can be made. If you'll notice, every 4th scan line on the screen is black, giving it a sort of retro appearance. However, part of the reason for this is that during the black scan line, the CPU is free to actually execute code instead of worrying itself with drawing screen data. However, it is possible to disable this feature, but first I'll show you the Mandelbrot demonstration. So this creates a fractal image on the screen, and it looks like it wouldn't take very long, but this actually takes quite some time. But one thing I wanted to show you is that if you press the select button on the controller, it will toggle the scan lines to a more full-looking mode at the expense of losing CPU cycles for program code. And this is clearly obvious on a program like this because you can see how much it slows down when this mode is enabled. Even in the faster mode, it takes almost 20 minutes to draw out this fractal pattern.
Hi, my name is Alina, and I would like to give you a few reasons why you should consider dating a young Slavic.
There are a couple of games on here. The first one is Snake. And I haven't entirely figured out the point of the game. I'm not sure if I'm supposed to be collecting these dots or avoiding them. The other game is called Racer, and I think the point is to simply see how long you can go without crashing. So I want to take a moment to talk about the programming language for the Gigatron. The CPU, if you can call it that, only supports 8 instruction codes. By coincidence, the PDP-8 was named what it was because it only supported 8 instructions as well. Even an old chip like the 6502 had 56 different instructions, and processors from Intel at the time had hundreds of different instructions. Writing code with only 8 instructions is certainly possible, but it would be very tedious. And so what they've done is they've created a virtualized environment. So imagine, for example, if you look at how computers were done in the 1980s, like an old Apple or Commodore. And if you imagine the hardware layer, this is the actual CPU itself, which must be programmed in machine language. Then they wrote a basic interpreter that is written in machine language but allows a basic program to run and a more friendly environment for the user to operate in. Well, the Gigatron does something similar to this. It also has the hardware layer, but then a virtual CPU is running on the hardware, which is written in the native machine code, but it interprets the user software, which is written in something called GCL, which stands for Gigatron Control Language. The language is still very similar to assembly language, but it does at least have 34 instructions, making it easier to code for. You might compare it to Steve Wozniak's Sweet 16 language in this regard. The CPU runs at 6.25 MHz, but by the time you take into account this virtual CPU system, you're probably getting something closer to 1 MHz, which is more similar to home computers from the 1980s. So while the Gigatron is pretty cool from a proof of concept and from an educational standpoint, it does have some flaws, which I'm going to have to point out. For one thing, it's not cheap. Now, computer manufacturers figured out a long time ago that the way to make computers cheaper was to reduce the chip count, not to increase it. And so this computer, with the number of chips it has and the size of the logic board and all the different holes and traces on it, means it's not cheap. It retails for 160 euros, which at the current conversion rate is almost 200 US dollars. And that in and of itself wouldn't be so bad, except the second problem. And this is, of course, just my subjective opinion, but the truth is, once you've finished assembling the computer and you've explored all of the built-in software, there's not a lot you can actually do with it. There's no keyboard interface, and there's no way to actually program the Gigatron from the computer itself. There is a feature called Loader on the main menu that will load new software in, but it requires using an Arduino and of course doing all of the coding on an actual modern PC. And so I think that's a big drawback and thus loses a lot of the...
Oh, I'll leave it there. So he has another video where he says, well, version, I think 2 or 3 of the Gigatron came out. It's the same hardware, but you swap out the ROM chip for another ROM chip. And then you get things like a basic interpreter, a few more games, a keyboard interface, and a few more things. So it becomes a more kind of usable computer. So, watch that other video if you are interested in that. And he said it's kind of expensive, but really you can purchase just the printed circuit board itself for $20, which seems like a steal. And then you can also buy a kit that has all the parts in it, or you can, if you're like me, you have all these parts actually just sitting around, so you can actually use some of the parts you've already got. And then you can build this computer for a little bit less. I don't think it actually costs $100 and something for all the parts. You could buy the parts for less than $100 yourself. So whoever's putting together the Gigatron kit is making a few dollars on top of that. So that's fine. If you just want to buy a kit, it has all the parts in it ready to go, then that'd be the way to go. But it's a very educational experience to be able to put together a computer, and the manual that describes how the computer is put together describes also how the computer works. And so there's a lot to learn from studying these older style computers rather than the newer ones. If you build your own PC, sure, you learn how to build a PC, but you don't learn a lot about how it actually works and how all the pieces, you learn how the pieces physically fit together, but you don't necessarily learn how does the video card talk to the processor, and how does the audio interface get information from the processor and ultimately from the programming. You don't learn any of that stuff when you just build a PC. But if you build a computer like this, there's instructions on how it's actually decoding your instructions and how it's executing them. And so it's a really great learning experience. So I kind of want to get the printed circuit board and start building up that computer and just try it out for myself. So with a newer ROM chip, you're basically swapping in a newer operating system. That's exactly what you're doing with that. Okay, well, we went way over, so that's it for today. When we come back next time, we are going to start doing more with what's called Boolean algebra, which is being able to take a Boolean expression and manipulate it. So be able to take a Boolean expression and do something with it as far as simplifying it or converting it or transforming it into something else. And then we'll also learn how to be able to take a truth table and build a minimized circuit without going through the laborious process of looking at the sum of products and then simplifying from there. I'll show you a visual way of doing it where you just put some dots inside of boxes. That'll actually be next week. And then you just look at that picture, put little circles on it, and then you've got yourself your minimized circuit, minimized expressions. That's really cool. Okay, So I'm going to wrap it up here. Thanks for sticking around, the few of you who are still here. And I will see you all next time. Have a great day. Take care. Bye-bye. And we got a few people on YouTube, so thanks for sticking it out also and watching that. Again, you can go find that video that I showed you, and you can watch part 2 of it. So I got to take off. Again, have a good day, everyone. And I will see you next time as well. Bye-bye.